This video is on units for heat, specific heat capacity, and then a formula that will actually allow us to calculate heat in a certain situation. Okay, so starting with units for measuring heat flow, there are two common units. The first one is the calorie, just like you're familiar with your candy bar wrapper saying so many calories. And calorie gets the abbreviation CAL. And the other one, which is the more common one that we will see with energy and heat, is the joule, and it gets the abbreviation capital J. Now, the joule itself is fairly small, so sometimes we'll see kilojoules, okay, which are 1,000 joules, just like the kilogram is 1,000 grams. If you need to convert between calories and joules, there is a conversion factor that says 1 calorie is equal to 4.184 joules. Not something to be memorized, it's just a way to convert between the two units. Okay, so from there we're going to talk about something called heat capacity and specific heat. So the first discussion here is the word heat capacity. And the heat capacity of something is defined as this. All right, so heat capacity is defined as the amount of heat that's needed to increase the temperature of some object by 1 degree Celsius. So this brings up a couple interesting points. One, it brings up the fact that there's no mass discussion here. So if you're talking about like heating water, it would take significantly more heat to raise a gallon's worth of water by 1 degree Celsius than it would say, a cup's worth of water. Okay, so that's something that we have to think about. And then it also has no discussion of who you're talking about. So composition comes into play here. It's going to take a different amount of heat to raise water's temperature than it is to raise iron's temperature. Okay, so this idea of heat capacity is a little bit vague because mainly it depends on how much substance we have. So, to be a little bit more specific, we define something called the specific heat capacity. And this is the one we'll be talking about. Specific heat or specific heat capacity gets the symbol capital C. And it is defined as almost the definition we just used with an extra addition. So your specific heat capacity is defined as the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. So now we can start to compare substances across the board because we also have a mass component of this quantity. Okay, so just so you know, the specific heat of water, which we'll be using a lot, is 4.18. And the unit here makes sense because it's joules per gram degree Celsius. See the amount of heat required to raise the temperature of 1 gram by 1 degree Celsius. So we'll be using this a lot. And there's a little bit further down your paper, there's a table of common substances and their specific heats. Notice this is in joules per gram degree Celsius and this one's in calories. Okay. Water's at the top of the list. Water is an interesting chemical, even though we think it's pretty boring, but there's a lot of chemical discussion as to why water has the properties that it does, and it has a very high specific heat. Okay, so from here, we have to talk about a chemical formula that is going to be very, very helpful to us in thermochem. And so that chemical formula looks like this. And some of these variables we already know. Okay, we already know Q, it's heat. We just learned C is specific heat. And most of the time, specific heat will be in joules per gram degree Celsius, which means my heat will be in joules. M is mass, which will be in grams. Sometimes in kilograms, we'll see that eventually. We just have to watch our units. And then delta T, so anything delta means change. So this is the change in temp. This is defined as T final minus T initial. Okay, and the units for delta T can be degrees Celsius, which is most common, or they can be Kelvin. Okay, and that's because a change in degrees Celsius is actually equal to a change in Kelvin. So if something's temperature raises by 5 degrees Celsius, it actually also raises by 5 Kelvin. We learned Kelvin a long time ago, where we said Kelvin can be calculated by adding 273 to Celsius. So the rest of this kind of discussion is about using this formula to solve for an unknown. Just like any other formula, if I have all but one of these components, I can solve for the fourth one. Okay, so we're going to be doing a little bit of a discussion on how to use this formula to solve some problems. Okay, so I have one. Oops, my page is cut off. I have one formula, and there it is. So let's do a couple practice, and at any point, I would recommend that you pause and try these on your own, maybe after the first one, see if you can get anywhere, and then of course you can listen to my explanation. All right, so the temperature of a 95.4 gram piece of copper increases from 25 degrees Celsius to 48 degrees Celsius when it absorbs 849 joules of heat. What is the specific heat of copper? So they're asking me for specific heat, which is C in my equation. So I want to solve this for C. I need to get rid of M and delta T. They're being multiplied. I'm going to divide. And so now I have C equals Q over M delta T. And all I need to do now is plug in my numbers. So my Q is 849 joules. My M is 95.4 grams. And I don't have a delta T, but I have a T final and a T initial. This is my T initial, and this is my T final, and so I can subtract that. I put this in my calculator. I round to sig figs, and to 3 sig figs. This is my number. With the units of, because nothing canceled, joules per gram degree Celsius. So that's the specific heat of copper. We could compare it to other common substances in the table. We find that it fits down here with the metals, which makes sense. Copper should have a low specific heat. It's a good conductor. It's way less than water. So that's my answer. Number 2 is very similar. So if you want to solve that one on your own, that'd be a good idea, but I will solve it, of course. When 435 joules of heat is added to 3.4 grams of olive oil at 21 degrees Celsius, the temp increases to 85. What's the specific heat? Same idea. I already have my formula solved from above. Q is 435 joules. My mass is 3.4 grams. And again, I have T initial of 21, T final of 85. This time I'm limited to 2 sig figs, so this answer to only 2 is actually 2.0. Again, joules per gram degree Celsius. Okay, number 3, how much heat is required to raise the temperature by 52 degrees Celsius of 250 grams of mercury. So how much heat? So they're actually asking me to solve for Q. I don't have to do any algebra here. I know the mass of 250 grams. I don't know C, but this is the specific heat of mercury. So if I go up to my table, I bet it's in there. Yep. So specific heat of mercury, we'll use the joules, so 0.14. And then this time, they didn't give me a T final or a T initial. They actually just gave me a delta T. Because see, to raise something by 52 degrees Celsius, that is the change. I don't really care where I started and where I ended, because I know the temperature went up by 52 degrees. Look at my units. Celsius cancels, grams cancels, leaving me only with joules. And two sig figs, again, here, will give me a heat of 1,800 joules. It came out to be 1,820, right? But to 2 sig figs, it'd be 1,800. And then the very last one is probably the hardest of them all. Oops. It says calculate the final temperature of a 355 gram piece of iron at 25 degrees Celsius that absorbs 7,500 joules of energy. So they want me to find T final, which is actually not in this formula. That's because it's embedded in delta T. So I'm actually going to do this in 2 steps. I'm going to solve this for delta T, and then I'll attempt to solve it for T final. So I need delta T by itself, divide by MC. Q is 7,500 joules. My mass was 355 grams. C of iron, again, I need to look up. 0.46. That's in joules per gram degree Celsius. My joules cancel, my grams cancel, leaving me only with degrees Celsius. I end up with a delta T of about 45.9. But be careful, because that's delta T and that's not what they asked me to find. We learned above that delta T is T final minus T initial. I'm looking for T final, so let's get rid of T initial by adding it. So T final will be delta T plus T initial. My delta T was just calculated, 45.9, and my initial temperature was 25. Gives me a number of 70.9, but I am limited to 2 sig figs here because of my energy. So if we're being specific, we should report my final temperature as 71 degrees Celsius. So just like any other formula, Q equals MC delta T can be used to solve for any unknown, provided that I have everything else, and provided that I can algebraically rearrange that equation to solve for what I'm looking for.